Here we go for lessons 26 and 27, friction. Friction is a force that always exists between any two surfaces in contact with one another, with each other. So there it is, your basic definition of friction. Some good notes on friction. Friction is super important in the world that we live in. We have two kinds of friction. We have static friction and kinetic friction. You can see that static friction is the friction that exists between two surfaces that are not moving relative to each other. And kinetic friction is the friction that exists between two surfaces that are moving relative to each other. So if you just think about the difference between those two, which one would be greater? Just think about trying to push a refrigerator. You've got a refrigerator in the middle of the room and you're pushing it across the room. What's more difficult? Pushing it once it's moving or getting it started moving? And the answer to that question is obviously once you get it started, then it has a little momentum, and it's much easier to push. And so the kinetic friction is actually a little less than the static friction. Okay, which your notes describe there very well. And also some very interesting things here about what causes friction. It's one of those things like gravity, where there's actually there's a surprising lack of knowledge regarding what actually causes friction. But let's get on to the good stuff here. Oh, very interesting. Did you know about tarantulas? And here we go with some formulas. Here it is. This is the formula for friction. The formula for friction is the force of friction. Oops. Force of friction equals this funny symbol, mu, the Greek letter mu, times Fn. Fn being the normal force, not the net force, but the normal force. And the mu, what is mu? Mu is a specific value and it's different for each type of surface on each type of other surface. So the mu value just describes how much friction there is between any two given surfaces. For example, the mu value between the example right here, a rubber hockey puck in the ice, is probably much less than the mu value for your car on the road, right? If you're driving your car and the mu value is low, it means you're going to be slipping and sliding around. So then we go. This is stuff you don't really need to know too much. But this table is interesting. So go to the table. Here are the mu values of static friction and kinetic friction for specific surfaces. You can see steel on steel has a relatively high value. Rubber on concrete has a very high value of 1. Not surprisingly, we want there to be a great deal of friction between the tires of your car and the road on which you drive. So it's not surprising that this one here is a very high value. Let's look at the chart to find the lowest one. What do you think the lowest one here is? Wood on wood, glass on glass, ice on ice? No, it's right down at the bottom. The lowest amount of friction is the synovial joints in humans. So in other words, your knees and your elbows have very little friction, which is great because if they have a lot of friction, then they're going to wear out, and then you can have all kinds of physical issues moving your arms and your legs and all the joints in your body. Okay, so and as you know, say you don't have to memorize that. Here we go. Let's get on to some problems that involve friction. A 12 kilogram piece of wood is placed on another piece of wood. There are 35 newtons of maximum static friction measured between them. Determine the coefficient of static friction between the pieces of wood. Okay, so in this question, we're asked to find mu. We don't know what mu is. Here is our formula. Fn equals mu, sorry, Ff equals mu Fn. Therefore, mu equals the force of friction divided by the normal force. And it tells us what the force of friction is right here, 35 newtons. The only thing we need is the normal force. So if you've got a piece of wood sitting on another piece of wood, the normal force is very simply equal and opposite to, is your normal force, equal and opposite to gravity. So your normal force is the same as mg. 12 times 9.81. Just put that in right here, 12 times 9.81. That into your calculator, and you are going to get 0.30. And the units for mu, for the coefficient of static friction, there are no units. And obviously, if you have force here divided by force, newtons divided by newtons, they cancel each other out, or they become one, essentially. So there are no units for the value of mu. Moving on, we have example number 2, which says I have a steel box sitting on a steel workbench and trying to push the box out of the way. Sketch a free body diagram of the box. So here's the box. It's sitting on a steel workbench. You see your free body diagram is I'm trying to push it out the way. So there's going to be an applied force going that way. The force of friction is the opposite. And then, of course, you have your normal force going up and your gravitational force going down. So there's our free body diagram. I push against the box with 25 newtons of force. Determine if anything will happen. So what I want to determine is the applied force of 25 newtons enough to overcome the force of friction. So the first thing I'm going to do is I'm just going to do this step by step. I'm going to find out what my normal force is. What is my normal force? My normal force is equal and opposite to my force of gravity, which is simply mg, which is going to be 10 times 9.81. You'll notice we're not using the negatives here. You can put the negative in if you want, but we know the normal force is going up. It's going to be positive, so I'm just going to leave it out. Theoretically, it should go in. So there's a normal force. What's the next thing we want to find? Well, we want to find out what the force of friction is. So step 2, the force of friction, because then if we find out what the force of friction is, we can determine if 25 newtons is enough to overcome that force of friction. Mu. Now, what do we use for mu here? A steel box on a steel workbench. And in any question of this nature, they will have to be given to you, the mu value. So we'll go back to here. We've got steel on steel. And we've got 0.74, 0.57. Which one are we going to use? One's static, one's kinetic. Well, in the question, it says a steel box is sitting on a steel workbench. So in other words, they're stationary. So we're going to use the coefficient of static friction, which was 0.74. 0.74 multiplied by the normal force. And we're going to get an answer of 72.52 newtons. Okay, so that's the amount of friction force is there. Is this 25 newtons going to be enough? No, not even close. So in other words, determine if anything will happen. The answer is no, nothing will happen. You need way more force. Now that actually rounds up to 73, because as you can see in the next question, it says determine if I push with a force of 73 newtons. 73 newtons. So for this one, we know that that's how much force, 73 newtons, is required to overcome the force of static friction. So we, at this point, want to determine how fast will it accelerate, determine what will happen. And we can just use a net force statement. And we know that the net force is going to equal the applied force plus the force of friction. This is our applied force, 73 newtons. Our force of friction is also 73 newtons, but it's in the opposite direction. Oops, I don't need to put the M there, but and we're going to get the answer 0 newtons. The answer is 0 newtons. That's not on, it's 0 newtons. So what will happen if the net force is 0 newtons? What's the acceleration? Obviously 0. So what will happen is nothing will happen. you've got enough force to kind of get it started moving, but it's not going to accelerate. So the answer to that question is what will happen, determine what will happen, and the answer is nothing. Again. But now we come to the last question, and the last question says if I push with 100 newtons of force, clearly we're past 73, so it's going to go. It's going to move this time. But what we have to acknowledge for this question, what makes this difficult, is that if it's going to move, everything else about the question has to change. So for example, the force of friction equals mu times Fn. Well, if it's moving, then 0.74 right up here no longer applies. We have to go now back to our kinetic, and we're going to have to use 0.57 instead. So we have to recalculate the force of friction. What was the normal force? 98.1. And that's going to give us 56 newtons. So now my friction force, because it's moving, because kinetic friction is less than static friction, my friction force is now 56 newtons. And then I can do what I did in part C. I can just say that the net force equals the applied force plus the force of friction. My applied force is 100 newtons. My force of friction is negative 56 because it has to be opposite the direction of motion, and therefore I get a net force of 44 newtons. And so that could be what answers the question. Determining will happen. Yes, 40 has a net force of 44 newtons. To be more specific and more to explain it better, we should find the acceleration. And the acceleration is going to be 44 newtons divided by the mass, which is 10, 4.4 meters per second per second. Okay, so the objects will accelerate at 4.4 meters per second. Okay, there's one more problem in this in lesson 26, but for that problem, we're going to make an entirely different video because it's far more complicated than you may think. So get ready for part 2 of this lesson.